So this is yet another side channel attack paper on BLISS. I think in this talk I'll describe an attack against a somewhat different part of the signing algorithm. So as you have seen in previous talks, people are getting serious about obtaining practical quantum safe cryptography, especially with the NIST competition coming up. And we actually have quite a few good candidates in principle. So we have many papers that describe a very good uh, uh, schemes with strong security guarantees, in particular based on lattices. But as Peter mentioned earlier, so many of these, so the analysis of these schemes in terms of implementation security is limited so far. We have various problems for implementing them, in particular with side channels. So in this talk, what I'm going to do is describe a new side channel attack on the BLISS signature scheme. And so we provide, actually in the paper, attacks on 3 parts of the signing algorithm. And in this case, I'm going to focus on rejection sampling. So we have 2 concrete targets against which we carry out our attack in practice. So one is an embedded device, an 8-bit AVR microcontroller. And there's an actual implementation for this type of devices in the literature. And we attack that using electromagnetic analysis. And then we also have an attack on the desktop, also against the strong swan VPN library. And this uses a pretty strong attack model, which we call branch tracing. I'll say a bit more about this later. And so what to obtain? So for this specific attack against rejection sampling, we obtain a full key recovery for a portion of keys which we call weak, which is not precisely defined sets, but it depends on your computational power. And in practice, for example, it's easy to attack at least about 7% of keys in BLISS1. And we use number theoretic techniques for this recovery. So to compare with the previous talk, so we have the same target, and in the BLISS signature scheme. And in particular, on the desktop, we also attack the strong swan library. But so in this talk, I won't talk about the variant called BLISS-B. Okay, so sorry, what's different? So at least in this talk, I discuss a different part of the algorithm. So not a sampling of the Gaussian randomness in the algorithm, but the rejection sampling step, which I'll describe. So we use different types of side channels. So EMA and branch tracing instead of cache attacks. So as I said, so on the desktop, so this branch tracing assume a very strong adversary. So in this sense, our attack on the desktop is weaker than the attack presented in the previous talk. And so our algorithmic techniques are quite different. So there are some advantages. For example, you need fewer traces for key recovery. Yeah, so in this specific attack, we are only successful against a subset of keys. You've heard about BLISS before. Let me recall a few things. So it's actually one of the top contenders for post-quantum signatures, although we've heard a very nice one at the start of this session. So this, as far as I know, this is probably the fastest post-quantum signature scheme. It was introduced at Crypto 2013, and it's implemented on various platforms, so the desktop, microcontrollers, and you have hardware implementations on FPGA. So it's in contrast with other proposals, we have code to work with. And it's deployed in that VPN library. So it works in this particular ring. So I consider ring elements to be polynomials instead of matrices, but it works the same. So the computations are carried out modulo some prime. So the secret key, as mentioned before, these are, you can see sparse ring elements. So polynomials with random coefficients equal in this interval. And there are not too many coefficients not equal to 0. And so the verification key is just the quotient of S2 divided by S1 up to sign. So you have to make sure that S1 is invertible mod Q somehow. If not, you restart. And you've seen the BLISS signature again. So let me emphasize some parts that are interesting for us. So you've seen the Gaussian sampling. That's the part that was attacked in the previous paper. So in our paper, we also have an attack on this, but a bit theoretical. You have special hash function here, which is interesting. So insofar as you've seen, this element C is something which is very, very sparse. So it has only a few coefficients equal to 1, and the rest is equal to 0. Then what you do is take those elements that you have generated, and you obtain basically the key, the signature, by multiplying the secret key by your element hash value C, and add the randomness Y to mask everything else. But if you do this, the scheme is not secure. So because it leaks in a statistical sense, it leaks information about the key. So what you have to do is rejection sampling, as I call it. So this specific step, where basically what this step does is make sure that if you pass it, then the elements Z1 and Z2 will have the same Gaussian distribution as the elements Y1 and Y2. If not, then you restart. And what's interesting is that you have many complicated nonlinear transcendental functions that are computed here. So for example, in this part, you compute the exponential, the inverse of exponential of minus this thing. So that's pretty complicated. This is a pretty complicated computation, and that's where we are going to collect our side channel information. All right. So okay. So that's the part I'm interested in. And so as I mentioned, so this rejection sampling is kind of a cornerstone of BLISS security. So this type of operation is what differentiates a scheme like BLISS, which is secure, from early attempts at lattice-based signature, like n-true sign, which was not secure at all because of the leakage on the secret key from the values of the signature. And so if you try to implement it in a simple way, like for example by computing your exponential function using floating point operations or things like this, it's going to be probably very inefficient, and especially as you have to compute everything with a high degree of precision for security. So what people use is a kind of optimized version of the rejection sampling. And the idea behind the optimization is to use iterated Bernoulli trials. So you have seen a bit of that. You have seen a bit of that algorithm before, because it's also used for generating the Gaussian randomness at the start. Okay, so thanks to that, so you can see that in the rejection sampling, sorry, you have some values here that are inserted. And what's interesting is that we will be able to recover the bits of that. So basically, you will learn that value from a side channel leakage. And you can basically read off this value, which is an integer, on, say, simple power analysis or simple electromagnetic analysis trace. And from a few of these, you will be able to recover, for example, So if S1 is the secret key, so you won't directly get S1, but you will get S1 multiplied by its complex conjugate, which is called something like the relative norm of the secret key. And that's interesting because using some tools from algebraic number theory, you can use that to retrieve S1. So again, so that's the Bernoulli sampling algorithm that looks like this. And what we're interested in especially is that, as you can see, there are operations that are carried out. So you iterate on the bits of the input. And some operations are carried out when the bits are 1, and not at all when the bits are 0. So it means that basically, just looking at power trace, you will learn when the bits of the input are 1 or 0. And so in this case, the inputs, it's basically the value I told you, so the squared norm of big S times C, up to some additive constant. So in practice, so if you execute that, so in our case on our AVR microcontroller, you can directly measure the electromagnetic emanation of the device during this Bernoulli sampling step, and you will obtain very quickly a trace here, where you have a peak of power of emanation when the corresponding bit is 1, which is when the device actually does something within the loop, and almost nothing when the bit is 0. And so in this case, for example, you recover this sequence of bits, and it corresponds to the value k minus this square norm, which is then equal to, which you can conclude is equal to 14,404. That's one of the practical examples we carried out. And so it may seem like recovering this sequence of bits is kind of a manual operation, but it's not. So it's a typical technique in side channel analysis. You can simply, for example, find a small pattern that is repeated at every step, and you pattern match on that, and you recover a peak at each, which is located once per iteration. So you can measure the timing between operations, and then find when you have a 1 or a 0, depending on if the timing is large or small. All right. So that's what you do on microcontrollers. So what about desktop machines? So it seems hard to carry out the same type of side channel analysis on desktop machines. So it has something. Things like this have been done to some extent in the past, but like the high clock frequency, for example, is a challenge when collecting those traces. Because of multitasking, you might be interrupted during the computation. So in this case, you don't get the full trace, and so on and so forth. And also the threat model is different. So typically, it's hard to suppose that you can come and put an electromagnetic probe against your machine. So it's a bit difficult to do the same thing on the desktop. So you would need other side channels more better suited to this setting. So a typical one would be cache attacks. But it seemed to us that cache attacks are probably difficult to mount in this setting for various reasons. Basically, in the previous talk, the same Bernoulli sampling was targeted, but the attack required a relatively small resolution, basically knowing whether there is a 1 at some point or not at all. For us, we really need to recover the exact value of the input of this sample Bernoulli X function. And because of that, it's probably difficult to do it with cache attacks, especially the table lookups involved in this algorithm involve tables which are small, so they fit in only a few cache lines. So it's probably difficult to do that. So what we do instead is give a lot of power to the attacker and use something called branch tracing. So what is that? So modern CPUs like Intel and AMD, they provide what's called instrumentation, for example, for performance profiling, that give you sort of meta information about things occurring on your processor. And so, for example, what you can obtain is information like source and destination addresses for all branch operations in a program. And this type of, so typically these are privileged metadata, but this can be exposed by the operating system. So in Linux, for example, it's called perf event, and you can access that even from user land. So for example, there's a program called perf that you can call, and this command line gives you basically a dump of all branch instructions carried out inside a specific PID. And so we do that on a running instance of a program compiled against the strong swan library. And we can collect those branch instructions. And in particular, we can identify in which case we take the branch corresponding to the if, matching on the each bit of xi of the input of our Bernoulli sampling algorithm. And this reveals the complete input for every signature that we generate. So we can completely recover the input of that function. So that's what the assembly code for that function looks like. And so you can see, so there's this if x and x mask, which corresponds to testing the varying bits of the value, the input x. And so there's a branch instruction here, and then whether, depending on whether the branch is taken or not, we know whether the corresponding bit was equal to 0 or 1. And so it's very easy to write the corresponding exploit if you want. Okay, so in both cases, we get something like this, and then we want to exploit it somehow to recover the secret key. So what we get, again, is this integer for each trace, for each signature for which you have a trace. So you have a sum like this, so S1 and S2 are the two components of the key, and you get something like the squared norms of the products S1C and S2C, where C is an element of the signature, so you know C every time, and it's different for each signature. So what this gives you, actually, so it's very easy to see, that this gives you linear equations on the coefficients of those two elements. So the S1 times S1 bar, so the absolute value of S1 as a complex number, and the same for S2. And so these two elements live in a space of dimension 256. So S1 itself is of dimension is in a space of dimension 512, but here you're in a subfield, in a quadratic subfield, if you want. And so as a result, this depends each on 256 coefficients. So, and you have two of them. So if you have twice, two times 256 linear equations, you should be able to recover these two values, these two real numbers in some sense. So for this to be true, you need the linear equations to be independent, but that's the case with high probability. Of course, it's just linear algebra, so it's very simple. And collecting 500 electromagnetic traces, for example, is very easy. Branch tracing is also quite simple. So, and then the problem you're left with is going from this element, it's called the relative norm, to the value S1 itself. And that involves some algebraic number theory. So it looks like this. You start with this, so you have this secret S, and what you know is the product SS bar. So this lives in a subfield, the so-called totally real subfield inside this cyclotomic field. And what you first do is from this element R, you map it to an integer, which is called the norm, the absolute norm, the algebraic norm of this element R. And so let's say, for example, that this algebraic norm is a prime. So this happens with a significant probability. So in that case, this prime so we can look at it inside this other field Q of I. So and you can notice that Q of I and this is basically the original field intersected with R. So these two generate the original field that you started from. So and inside Q of I, such a prime necessarily splits as a product of two like this. So it's a so-called Gaussian integer prime, and its conjugate. So you have a splitting like this, and because of that, I can look, for example, at what I get by intersecting pi and R inside the ring of integer, the ring R inside of this field. So it's an intersection of so-called ideals, and what you can easily prove is that the ideal generated by S must be either of those two intersections, either the one coming from pi or the one coming from pi bar. So what, in the end, you obtain the ideal generated by S. But so in general, it's hard from a so-called principal ideal to recover the element, the generator. But in this case, it's easy. There's a well-known algorithm to do that. It's called Gentry-Seed law. So it's hard in general, but it's easy when you know this additional information called the algebraic norm. And so at the end, you obtain the number S up to multiplication by a root of unity. So okay, so this applied if the absolute norm P was a prime, but it generalizes easily as long as you can factor this absolute norm. And then what you get at the end is, depending on the factorization, you get a small number of candidates for the value S1. So it's easy to check if a given candidate is correct. What you just do is compute the corresponding candidate for S2, which is just A times S1, mod Q. And this one should have small coefficients and should be sparse. And so if it is, it's probably correct. And if it's not, you have to try again among the other candidates that you have. So I said that you get it up to multiplication by root of unity, but it's not a problem. So a root of unity is just an element like plus or minus x to the n, and multiplying that by that just shifts the coefficient up to sign. And so it gives you, if you multiply S1 and S2 by the same one, you obtain something which is a perfectly equivalent key to the one you started from. So recovering up to a root of unity is just as good as recovering the exact one. So this works for what I call weak keys. So this just means that you are able to factor the absolute norm. So there are many examples of such things. So for example, you can look at the keys for which the absolute norm is the multiple of a large prime times something which is small enough that you can factor it. For example, who has small prime factors. So for a typical for BLISS parameters, for example, we easily find that about 3.7% of keys have an S1 which satisfies this condition, and you can apply it on S2 as well with the same probability. So about a bit more than 7% of keys are easily recovered in that way. And it takes, so what's long about the attack, what takes a lot of time, is this Gentry-Seed law algorithm that I mentioned. But even on 512 bits, it takes about 38 CPU days, which is quite reasonable in practice. All right, so what are some possible countermeasures? So what you could do, as I mentioned, is compute the rejection sampling with a floating point arithmetic, for example. But that's pretty slow, especially as you need very high precision. And also, you don't really know that your in most cases that your floating point arithmetic is constant time, for example, so it could cause other issues with side channels. So I wouldn't recommend trying this. So the previous talk also mentioned using constant time Bernoulli sampling. I think it's probably a good idea anyway. So you can do it. The overhead is quite small, so it's about at most 2 times longer. But the problem is that it's probably fragile in some sense that you have to trust your compiler not to insert time dependencies that are not apparent from the code. So again, like the previous talk, I would recommend considering a scheme with a simpler structure. Against the very complicated nature of the rejection sampling is caused by the fact that you have Gaussian distributions for the masks Y, and using uniform distributions instead results in schemes that are probably stronger against stations, so like GLP and dilithium. So in the paper, we present 2 other attacks on BLISS, one against the Gaussian sampling and now one against the polynomial multiplication. I won't go into that. And just mention as a conclusion that, okay, so post-quantum crypto is a hot topic. Physical security of those post-quantum schemes is a nascent research area that has many interesting problems. Open problems, and maybe avoiding Gaussians in lattice-based schemes is a good idea. Thank you very much. Yeah, so I mean, it does address the specific attack technique that we proposed. Of course, so just disallowing this type of branch tracing is, I mean, it's sort of it's tricky. So on the one hand, you could think of acquiring the same side channel information through different means, and that's quite possible. So maybe cache stacks don't have enough resolutions, but that's a technical problem that might be overcome somehow. And another issue is that so it depends on how you try to protect this access to those branch tracing information. So for example, in Linux, so normally you're only allowed to carry out this branch tracing operation on a process ID from the same user. That's the standard rule. However, until I think May of this year, there was a bug in race condition in the kernel that caused basically any user to be able to carry out this operation. And as a result, anyone, also a completely different user, could be able to access this. So this tends to be a bit fragile to protect in those kind of ways.